In this video, we're going to talk about what's probably the most common type of machine learning problem, which is supervised learning. Define supervised learning more formally later, but it's probably best to explain with an example what is supervised learning. We'll do the formal definition later. So let's say you want to predict housing prices. A while back, I actually had a student collect data on housing prices from the city of Portland, Oregon. And so let's say you collect a data set that looks like this. Here are my axes. On the vertical axis, let's say I plot the price of a house in thousands of dollars. So, you know, there are, what, 100,000, 200,000, 300,000, $400,000 houses. And on the horizontal axis, let's say I plot the size of the houses in square feet. So these are different values on the horizontal axis. If you collect a data set, you know, your data might look like this, right? So maybe you have a data set of, you know, different houses, sizes, and how much they cost. Now, let's say you have a friend who has a house that is 750 square feet, and they want to know how much they can sell this house for. So how can a learning algorithm help you? Well, one thing a learning algorithm might be able to do is, say, fit a straight line to this data. For the straight line, it looks like that. And based on this, it looks like, you know, maybe you can expect, maybe your friend can expect to sell the house for, what, maybe about $150,000, right? But it turns out learning algorithms, well, maybe this isn't the only learning algorithm we can use. Maybe there's a better one, and maybe we don't want to fit a straight line. Maybe we want to fit a quadratic curve to this. And if you do that, maybe this curve actually fits the data better. And if this second line is better, then, ooh, that's pretty nice. Maybe your friend can sell the house for, $200,000 instead. So one of the things we talk about later as well is how to choose or to, how to decide. Do you want to fit a straight line or do you want to fit a quadratic function as a data? But both of these would be examples of learning algorithms. So this is an example of supervised learning. And the term supervised learning refers to the fact that we gave the algorithm a bunch of right answers. We gave it a data set with the right answers, meaning the correct housing prices in the data set, and we asked the algorithm to produce more of these sort of, quote, right answers of what are the correct housing prices. More formally, in supervised learning, the learning algorithm is given data in which it is told the correct answer for each example. It's told the correct answer that we're trying to predict. To give a little bit more terminology, this is also called a regression problem. And by that, I mean that we're trying to predict a continuous valued attribute. We're trying to predict a continuous valued price. And I guess technically, maybe prices can be rounded off to the nearest cent. So maybe prices are actually discrete value, but we usually think of price of a house as a real number, as a continuous valued number. And the term regression refers to when we're trying to predict a continuous value attribute. Here's another supervised learning example. Some friends and I were actually working on this earlier, but let's say that you want to look at medical records and try to predict if a breast cancer, or actually a breast tumor, is malignant or benign. So, if someone discovers a breast tumor, so like a lump in their breast, right, a malignant tumor is one that's harmful and dangerous, whereas a benign breast tumor is one that's harmless. So, so people obviously care a lot about this. And let's say that, again, you collect a data set, like so, and let's say that on the horizontal axis, I'm now going to plot, the size of the tumor, and on the vertical axis, I'm going to plot, is this a malignant tumor or not? And so malignancy takes on only two values, right? It takes on one, which we want to use to denote the yes value, or it can be 0, or denote the no value. And let's say my data set looks like this, right? So I have some examples of tumors with this tumor sizes that were not malignant, so at 0, vertical axis is 0. And I also have some examples of breast tumors which did turn out to be malignant. That maybe looks like this. Okay, so I have five examples of malignant and 5 examples of non-malignant. And let's say you have a friend with maybe tragically a breast tumor, and let's say their tumor size is this. Then maybe what you want to do is estimate what is the chance that their tumor is malignant versus benign. So to introduce a bit more terminology, this is a classification problem as opposed to a regression problem. And the term classification refers to the fact that we're trying to predict a discrete valued attribute. We're trying to predict a discrete value output, 0 or 1. Right? In this example, the output takes on 2 values, 0 or 1. In some examples, if we have a small number of discrete valued outputs, maybe if it takes on values 0, 1, 2, 3, if there are like maybe 3 types of breast cancer tumors. So if you have a small number of possible outputs, but discrete value ones, then we call that a classification problem. So if you have like no tumor, or tumor type 1, or tumor type 2, or tumor type 3, that would be a classification problem as well. Let's see. It turns out in classification problems, there's actually another way to plot this data. So I'm going to just use a slightly different symbols to plot this data, which is if tumor size is the attribute or feature that I'm going to use to predict malignancy or benignness, I can also draw my data like this. I'm going to use different symbols to denote my positive and negative examples. Okay, so instead of drawing crosses, I'm now drawing zeros or drawing O's for the benign tumors, and I'm going to use crosses to denote my malignant tumors. So this axis is my tumor size. Okay, I hope this figure makes sense, right? All I did was I took each of these examples and I just copied them down here, right, with different symbols depending on whether it's malignant or benign. Now, in this example, we use only one feature or one attribute, namely tumor size. We use only tumor size to predict malignancy or benignness of a tumor. It turns out that in other machine learning problems, we may often have more than one feature or more than one attribute. Here's an example. Let's say that instead of knowing only the tumor size, we know both the age and the tumor size. So in this case, you may have a training example that looks like this, where again I have O's to denote the benign tumors, right, and crosses to denote the malignant tumors in this maybe slightly made up example. Okay, and so given a data set like this, a learning algorithm may decide to find a straight line like that to try to separate the malignant and benign tumors. And so if your friend's age and tumor size falls here, let's say, then hopefully theirs is more likely to be a benign one, right? More likely to be a non-malignant, more likely to be one of the circle types. In this example, we had 2 features, namely the age and the tumor size. A few of my friends have actually worked on the breast cancer prediction problem for real, and it turns out that for when you're actually doing this in practice, you often have many other features. So you have features like clump thickness, it's a measure of how clumpy the breast tumor is, uniformity of cell size, what else? Uniformity of cell shape, and so on. And when using learning algorithms to predict these things, you can end up having a lot of features. And one of the most interesting learning algorithms that we'll learn about will be a learning algorithm that can deal with an infinite number of features. right? So on this slide, I've listed 3 or maybe 5 age, tumor, 3, 3, 4, 5 different features. But it turns out that for some learning problems, what you really want to do is not use 2 or 3 or 5 features, but instead what you want to do is use an infinite number of features, so that your learning algorithm has a lot of different attributes, a lot of different features, a lot of different cues with which to make its prediction. So how do you deal with an infinite number of features, right? If you have an infinite number of features, I mean, how do you even store an infinite number of things on a computer? Your computer's going to run out of memory. But when it turns out, when we talk about an algorithm called a support vector machine, there'll be a neat little mathematical trick that lets us use a computer to deal with even an infinitely, imagine I didn't just write down 3 features, but I were to write down an infinitely long list of features. It turns out we'll talk about an algorithm that can deal with that. So just to recap, we talked about supervised learning, and the idea is that in supervised learning, in every example, we're given the quote correct answer, the correct output value that we're trying to predict, such as the price of the house or whether a particular tumor is malignant or benign. We also talked about the regression problem, where the goal is to predict a continuous valued output, and the classification problem, where the goal is to predict a discrete valued output. So here's a quick wrap-up question. You're running a company and you want to develop learning algorithms to address each of 2 problems. In the first, you have a large inventory of identical items. So imagine you have thousands of copies of some identical item that you want to sell, and you want to predict how many of these you'll sell over the next 3 months. In the second problem, you have lots of users and you want to write software to examine individual customer accounts, and for each account decide if each account has been hacked or compromised. So for each of these, would you treat it as a classification problem or as a regression problem? The video will pause in a couple seconds, and when it does so, please use your mouse to select which one of these 4 you think is the right answer. So hopefully you got that the first problem, well, I would treat that as a regression problem, because if we're trying to predict values from 1 to 1,000, right, number of items to sell, that's easy to treat that as a discrete value, as a real value output, or continuous value output. It's a regression problem. The second one, for each of the customer accounts, I want to decide if it has been hacked or not hacked, right? So maybe if I use 0 to denote not hacked and 1 to denote hacked, then for each user account, I'm trying to predict 0 or 1. So that's a small number of discrete values, and so the second one, I would treat it as a classification problem. So that's it for supervised learning, and in the next video we'll talk about unsupervised learning, which is the other major category of learning algorithm.